Hello, this is the first chapter of alcohols, phenols and ethers. So first of all we have to know what is alcohol, okay, and after finishing the discussion related to alcohols there will be discussion next to related to phenols, and after that related to ethers. So alcohol is any organic compound in which hydroxyl group, that means OH group, that will be attached to carbon atom, and this carbon atom, it will be an alkyl group or it may be some substituted alkyl group. Fine. So that in general how we write alcohol, it is written as ROH, where R is alkyl group or substituted alkyl group. The general formula for a simple acyclic alcohol, remember acyclic alcohol, that means it will not have any ring type of structure. In that case the general formula will be CnH2n plus 1 and OH group. Fine. Now when we will discuss IUPAC nomenclature, then also you will see that here the suffix that is used is OL, that is all, and it is according to the official IUPAC chemical name which is used for all the alcohols. Now as alcohol is containing OH group and it is attached to some alkyl or substituted alkyl group, so basically alcohol contains two parts. One part is alkyl group, that is the R group, and the other part is hydroxyl group, that is OH, and properties will be related to that is mainly because of this presence of OH group. So they exhibit a unique set of physical property as well as chemical properties, and this is specially because of this hydroxyl group. Okay, so this group is polar in nature and it is responsible for the polarity of the alcohol, because if we focus on the alkyl part there is no polarity. Okay, it is only because of this OH group. Now three major subset of alcohols we can have: primary 1 degree, secondary 2 degree and tertiary 3 degree, and it is based upon the number of carbon atoms the carbon OH group's carbon is bonded to. That means OH is attached to some carbon, and this carbon with which OH is attached, this carbon is attached to how many carbon atoms, depending on that we can call it 1 degree alcohol, 2 degree alcohol or 3 degree alcohol. So if it is attached to 3 carbon, that is the carbon with which OH is attached, then it will be called 3 degree or tertiary. If it is attached to 2 carbon and 1 hydrogen, it will be secondary, and if it is attached to only 1 carbon and 2 hydrogen, it will be called primary or 1 degree. Now the simplest secondary alcohol that is possible is isopropyl alcohol, because carbon with which OH is attached, this carbon must be attached to more carbon, that means minimum 3 carbon must be present, and this type of group, that is 2 methyl group attached to carbon, that is known as isopropyl group. So that is why the name of this alcohol is isopropyl alcohol. IUPAC name is propan 2-ol, because it is a 3 carbon chain and in the middle carbon, that is at the 2 carbon, there is OH group present. So here we have general expression for 1 degree, 2 degree and 3 degree alcohol. See, this is the carbon with which OH is attached, and this carbon is attached to 1 R group, that means 1 carbon and 2 hydrogen, so that is why it is 1 degree. Then in case of 2 degree, this carbon is attached to 2 alkyl group and 1 hydrogen, so it is 2 degree. And the tertiary alcohol, it is attached to 3 alkyl group and there is no hydrogen, so it is tertiary alcohol. So here R is alkyl group, or it may be hydrogen also. So in that case it is actually not even primary alcohol, then it will be the simplest example of alcohol, which is the first member, that is methanol, CH3OH, and R2, R3, all these are R1 alkyl group. So the isopropyl alcohol, this is the structure, and the simplest tertiary alcohol that is possible, which is 2-methyl propan 2-ol, because now the carbon with which OH is attached, it will be connected to 3 more carbon, That means minimum 4 carbon must be present. So that is why the simplest example for 3 degree alcohol is tertiary butyl alcohol or 2-methyl propan 2-ol. So 2-methyl propan 2-ol, why it is so? Because it is 1, 2, 3. This is the longest chain, and at 2 position there is methyl substituent and also OH, which is the main group. So that is why the suffix we are using ol. Suffix means the term with which the name is ending, and methyl is substituent, so that is why it is the prefix. 2-methyl, methyl is the prefix, 2-methyl propan 2-ol. So these two are the examples of simplest secondary alcohol and tertiary alcohol. And simplest example for primary alcohol will be, that is the carbon it is attached to only one carbon, is obviously CH3CH2OH. Next we will do the classification of alcohol, but remember classification may be done from different point of view. It can be classified based on the number of hydroxyl group. That is one way by which you can do the classification. Another way also by which you can do the classification is the nature of carbon to which the functional group is attached. So already you have seen the 3 examples, 1 degree, 2 degree, 3 degree. So that is also one kind of classification of alcohols we can see. Fine. So classification based on the number of hydroxyl group, because OH group is, when it is present it is alcohol, fine, but it may be more than one OH group. Okay. So depending on how many OH groups are present, sometimes the chemical properties, physical properties, these also changes. So that is why we will also do the classification based on the number of hydroxyl group and nature of carbon to which functional group is attached. Now when we are talking about nature, again under this category 2 types possible. One is whether the carbon is primary, secondary, tertiary. That we have already seen in the last slide. Another possibility, that is also nature of carbon, whether the carbon is sp3 hybridized, sp2 hybridized or sp hybridized. Depending on that also classification is possible. So here we have this flow chart. Alcohols, first we will do the classification based on number of hydroxyl group. So if it is containing only one OH group, it will be monohydric alcohol. If it is containing more than one OH, that is minimum 2 OH must be present, then only you can call it polyhydric alcohols. Fine. Examples of polyhydric alcohols: dihydric alcohol, that is the simplest example. Here we have ethane 1,2-diol, which is also known as glycol. Ethane because it is containing 2 carbon, and 1 and 2 position there are 2 OH group. Then trihydric alcohol. So now we have total 3 carbon, and all the carbon there is presence of OH group, and this is known as glycerol. IUPAC name is propane 1,2,3-triol. Then we have another example where you can see total how many OH groups are present: 4, 5, 6. That means 6, and this is known as sorbitol. Fine. So all these are examples of polyhydric alcohols. Now come to this left hand side, that is monohydric alcohols. Now this single OH group that is present, as it is single, so we are calling it monohydric. Now this single OH group, it can be attached to sp3 hybridized carbon atom, or it may be attached to sp2 hybridized carbon atom. Okay, that is vinyl alcohol. So when it is attached to sp3 hybridized carbon atom, then how many possibilities are there? See, OH group can be attached to simple alkyl group, that is no unsaturation is there. Another possibility is OH group is attached to an allyl group. Now allyl group is CC double bond then carbon. So here the OH is attached to sp3 hybridized carbon because this carbon is sp3 hybridized, but after that there is CC double bond, so that is why it is allyl alcohol, because allyl group is present. And the third possibility where OH group is attached to sp3 but it is benzyl group. Now benzyl group is phenyl ring, and after that there is CH2 and then OH. So see, this is also sp3 hybridized carbon with which OH is attached, but this is called benzyl alcohol because of the presence of this benzyl group. Benzyl group is PHCH2 group. So under this category where OH is attached to sp3 hybridized carbon, you can have three possibilities. And if it is attached to sp2 hybridized carbon atom, so this is the simplest example that is possible. So try to understand the difference between allyl alcohol and vinyl alcohol. Vinyl group is CC double bond and OH group is directly attached to sp2. But when it is allyl, then CC double bond, after that there is sp3 hybridized CH2 and then OH is attached. Okay, so this is the difference. Now this example, though we have already discussed it about 1 degree, 2 degree and 3 degree in the last slide, but remember this is also another kind of classification which is, you can call it as if it is depending on the nature of carbon with which OH is attached. So 1 degree alcohol, this is the simplest example possible, ethanol, because if you consider the first member of alcohol, it is methanol, and here methyl group only one carbon is present which is not attached to any carbon, it is attached to 3 hydrogen. So this is not 1 degree alcohol, so simplest example possible is ethanol. Next we have prop 2-in-1-ol. So this is also actually allyl alcohol. See, this is actually this molecule. Then we have phenyl methanol. This is nothing but benzyl alcohol, PHCH2H. But why we are calling it in this way, phenyl methanol? Because it is actually methanol derivative. Methanol is CH3OH. But if you replace one hydrogen from this methyl group by a pH group, that is C6H5, so it will become the derivative of methanol. So that is why it is called phenyl methanol. 2 degree propan-2-ol, the simplest example possible that we have seen in the previous slide. And here we have another example of 2 degree alcohol, but 3-in-2-ol. Because the longest chain, if you choose, it is 1, 2, 3 and 4. So at 3 position there is double bond, so 3 in 2 position all. And if it is phenyl group, now it is 1-phenyl ethanol. See, now it is the derivative of ethanol, because ethanol is CH3CH2OH, and if you remove one hydrogen from this CH2 and you replace it with C6H5, it becomes 1-phenyl ethanol, that is the derivative of ethanol. 3 degree alcohol, simplest example, 2-methyl propan-2-ol, but other 2 examples that are possible is, now we also have CC double bond attached to this carbon with which OH is attached, but it is 3 degree. Why? Because the carbon with which OH is attached, that is attached to 3 more carbon, so that is why it is 3 degree. And another example is 2-phenyl propan-2-ol. So in propan-2-ol, CH3, CHOH, CH3, but if you replace this H, that is see, this is propan-2-ol, but if you remove this H and if you place a phenyl group, it will be called 2-phenyl propan-2-ol. Fine. So all these are the examples of different types of alcohols, and remember classification can be done depending on how many OH groups are present, that is monohydric, polyhydric, or it may be depending on the nature of carbon with which OH is attached. Fine. Structure of alcohol. In alcohol there is carbon and also oxygen. Now both shows sp3 hybridization, though it is true that it is not the necessary condition, because it may be sp2 also. For example, if it is vinyl alcohol, then it will be CH2 double bond CH OH. Fine. So in this case we do not have any sp3 hybridized carbon, but here this statement is written because in most of the cases you will see that the carbon with which OH is attached is sp3 hybridized. Okay, in general. Now carbon and oxygen both are sp3 hybridized. Now come to carbon first. Carbon, it is from group 14. Outermost electronic configuration is 2s2 2p2. And if we consider the full electronic configuration, it is 1s2 2s2 2p2. So this is the ground state. But if it is in excited state, then this pair will be broken and this electron now transferred to 2pz. Okay, so now 2s, 2px, 2py, 2pz all are carrying one electron. So all these four, that is sp3 hybridization when it will take place, that means 1s and 3p, it will be hybridized and there will be formation of total 4 sp3. Fine. So all these 4 sp3 hybridized orbitals will be having one electron in each, and each of these sp3 orbital will be used for formation of sigma bond. Okay. So I am taking the very simplest example. Suppose we have ethanol, CH3, then CH2, OH. So here this carbon, it is attached to one oxygen, one carbon and two hydrogen. So basically this carbon is having 4 covalent bond, and this carbon, I am talking about this carbon, it will use 4 sp3 hybrid orbitals for formation of these 4 covalent bonds. Okay. Now come to oxygen. Oxygen is from group 16 and the general electronic configuration is 2s2 2p4. In case of oxygen, here also we will have sp3 hybridization, but out of 4 sp3 hybrid orbitals, all these sp3 hybrid orbitals, obviously unlike carbon, it will now not be used for 4 covalent bonds because oxygen is having only 2 bonds. Okay, so 2 sp3 hybridized orbitals will be left. So these will basically carry the lone pair of electrons. So see, oxygen 2s2 2p4. Fine. And after hybridization, that is if we combine all these together, there will be formation of total 4 sp3. Now 2 sp3 that will be used for sigma bond formation, because look at this oxygen, it is attached to one hydrogen and one carbon, that means 2 sigma bonds are present. So these two will be used for 2 sigma bond formation, and other 2 sp3 hybridized orbital that will basically carry the lone pair. Okay, so these two are lone pair. These two completely filled orbitals in oxygen atom do not take part in bonding. So these two are not taking part in bonding, and as a result what will happen, now there will be repulsion between these two lone pair. Okay, so if you look at the configuration of oxygen in this very simple formula of alcohol, that is ROH. So here oxygen is attached to carbon and one hydrogen, and here we have 2 sigma bond, and 2 sp3 hybridized orbital will be used, and other 2 sp3 hybridized orbital that will carry the lone pair, but there will be repulsion between these two. Okay, and as a result the bond angle of COH bond, now it will be slightly lesser than the tetrahedral angle, because the standard angle for sp3 hybridization, that is tetrahedral geometry, it is 109 degree 28 minute. But in this case, because of the repulsion between these two lone pair, what will happen, now this angle between carbon O and H, that will shrink to some lesser value compared to 109 degree. Fine. So here we have one example of isopropyl alcohol. See, this red atom is the oxygen. So this is oxygen, this is H, and this total part, this is equal to R. Fine. So this is one methyl group, this is another methyl group, the black atom is carbon and the grey atoms are hydrogen. There is one hydrogen attached to this carbon, so this total group, it will be R. So you can compare this, there will be actually 2 lone pair. Okay, there will be repulsion between this lone pair. As a result, the angle between these carbon, oxygen and hydrogen, this angle will be now lesser than 109 degree 28 minute. Fine. After structure of alcohol, next we'll see the IUPAC nomenclature for alcohols. Now when it is very simple alcohols, then the common names, they are used most often. Okay, that is in day-to-day life, it is simpler for, it will be easier for us to use all these names if it is simple alcohol. But if it is having very large structure or so many substituents are there, some branching is there, so obviously we cannot use the simple name. Fine, in that case IUPAC name we have to use. Now when we are talking about simple alcohols, then we will see how we can use the common names. So for example, suppose we have ethyl alcohol. So in this case what we are doing, we are seeing it is consisting of two terms, ethyl and alcohol. So simply it is the name of the alkyl group first, followed by the word alcohol. So alcohol we have to mention because of the presence of this OH group, but first we will write the name of the alkyl group. Come to the second example. Here the alkyl group is isopropyl group. Isopropyl group is Me2CH. So that is why the name is now isopropyl alcohol. Now come to the third example. Here we have total 4 carbon, but see, this is isopropyl group and this is present. So this is isopropyl group, but actually it is consisting of 4 carbon. So that is why the name is isobutyl alcohol. Tertiary pentyl alcohol, total number of carbon 5. Okay, and this carbon is tertiary alcohol, that is attached to 3 more carbon, so that is it is 3 degree. So it is called tertiary pentyl alcohol. Next we have some benzyl alcohol derivative. Benzyl alcohol is PHCH2H, but now NO2 group is attached to 4th position of CH2H group, so that is why it is para-nitrobenzyl alcohol. So see, again we are using the alkyl group and then we are writing the term alcohol. Next we have OH group is attached to this carbon, so that is why it is alpha. With respect to OH, this is alpha position, this is beta position. Okay, so alpha position, there is presence of phenyl group, so that is why the name is alpha phenyl ethyl alcohol. Okay, so see, this part is the alkyl group. Suppose the alkyl group is CH2CH3, then it is simply, the name is ethyl alcohol. That is the first example. But here one hydrogen is replaced by phenyl group, and which hydrogen? It is alpha hydrogen with respect to H. So that is why alpha phenyl then ethyl alcohol. Okay, so in this way we can use the common names. That is, you have to write the alkyl group first, followed by the word alcohol. But what about the structures when it is not simple, when it is there is some complicated structure, some branching is present? So now we have to follow the IUPAC rules. So the general rules that we follow for any IUPAC nomenclature, not just for alcohols, here also you will see the rules are same. So first what we do, we choose the longest continuous chain of carbon atoms, and obviously this longest chain will contain the functional group. Fine, and depending on how many carbon atoms are present in this longest chain, root word will be selected. Okay, next step is number the carbon atoms in the chain so that the carbon which is carrying the OH group, it will be given the lowest number possible. So after choosing the longest chain, next thing that you have to do, you have to put numbers, but not arbitrarily. You have to put the numbers in such a way so that the carbon with which OH is attached, that will be given the lowest number possible. Then the third step, if there is any other substituent, suppose some methyl substituent or some halogen substituent is there, so in that case you have to mention that. So ultimately, if we take all the rules together, first we will write the prefix. Prefix means if there is any substituent. So suppose if there is methyl group at 3 position, it will be 3-methyl, and that is the prefix. Fine. Then the root word, that is how many carbon atoms are present in the longest chain. After that, suffix. But suffix may be 2 types. It may be primary suffix and it may be secondary suffix. Okay. So when we will take the example, it will be clear. There is nothing difficult in it. And prefix is substituent. Then root word, it is the longest chain. Then primary suffix, if there is any unsaturation present or not, that is the double bond or triple bond is present, that we have to mention. And that will be treated as suffix, but it is primary suffix. And finally, OL, which is used for alcohol. And this is the term with which we are ending the name. So that is why it is suffix. Prefix means at the beginning, suffix means at the end. Now look at these examples and try to understand that here the rules that we have mentioned. That is first prefix, that is substituent, then root word, longest chain, primary suffix, secondary suffix. So here we have the columns, and where prefix is mentioned in the first column, then root word, primary suffix and secondary suffix. And in the leftmost column we have the compound with the common name, structural formula, and also at last the IUPAC name. So this molecule is CH3, CH3, OH group is attached at 2 position. Common name is isopropyl alcohol, that we have already seen in the last slide, right? But how we are using the IUPAC name? First, prefix with position number, but we do not have any substituent, because the longest chain, that is 1, 2 and 3, there is no other substituent. So that is why there is no prefix. Fine. Then root word, 3 carbon, so that is why it is prop. Primary suffix, there is no unsaturation, so it is N. So ultimately it will be written as propan. And secondary suffix, it is always all, which is at 2 position. So the name is propan 2 all. Okay. And be careful, it is not PANE, it is PROPAN, then hyphen. Then tertiary butyl alcohol, so this is the common name. Remember common name how we write? First alkyl group and then we write simply alcohol. But what will be the IUPAC name? So first choose the longest chain, 1, 2, 3. So here we have one substituent which is CH3, and this is present at 2 positions. So now we will have prefix which is 2-methyl, that is a substituent. Root word is same, just like the previous example, it is prop. Again there is no unsaturation, so it is alkane, ANE and 2 all. Third example, this group is altogether it will be written as neopentyl. Okay, so remember it is 5 carbon and but it is 1 degree alcohol, because the carbon with which OH is attached, this is attached only to 1 carbon. So don't think that it is tertiary alcohol. It is not tertiary alcohol, because carbon with which OH is attached, it is attached only with 1 carbon. Fine. So this group is neopentyl group. But what about the IUPAC name? So first you will choose the longest chain in such a way so that it can contain the OH group. Okay. Then numbering will be done in such a way so that the carbon with which OH is attached, that is this carbon, it will be given the lowest number possible. So here it is 1, then 2 and 3, and at 2 position there is 2-methyl group. That means 2 substituents are there. So now the prefix is 2,2-dimethyl. Other things are same, but it is 1 all, it is not 2 all. Okay. Some more examples. Isobutyl alcohol. So this is isobutyl group. Remember we have already seen this example, but now we will see how will be the IUPAC name. Longest chain, this is the longest chain. Put the numbers in such a way so that the carbon with which OH is attached is given the lowest number possible. So this is the lowest carbon, lowest number carbon, then methyl group is attached. So we will have prefix 2-methyl, then prop N 1 all. Next example is benzyl alcohol. Now mostly we use the common name, but if it is asked that what will be the IUPAC name, now see, this is prefix is now phenyl, so as if this is the substituent, because one of the hydrogen of methyl group, now it is replaced by phenyl, so it is the substituent. But root word is single carbon, meth. It is alkane, there is no unsaturation. Unsaturation is present in benzene ring, but in the longest chain there is no unsaturation. Though Longest chain is containing only one carbon, but still it is the convention we say it as longest chain, and it is containing only one carbon. It is alkane, so N and all, because there is only single carbon, so you don't have to mention any position. Then allyl alcohol, remember this type of structure. But when we will decide the IUPAC name, longest chain we have already chosen, but there is no substituent, so that is why there is no prefix. Longest chain is containing 3 carbons, so it is prop, but 2 position there is unsaturation. So now instead of writing N, we will write in, and we will also mention the position of the in. It is 2 in and 1 all. Next, cyclohexyl alcohol. It is a common name because cyclohexyl is the alkyl group and then alcohol. And here we do not have any substituent, and root word, though it is ring structure, so you may have some difference with the rules that we have already discussed, but see, it is more or less same. Cyclohex, that will be treated as the root word because it is derivative of cyclohexane. Fine. There is no unsaturation, so N and all. We don't have to mention the position because all the carbons in the cyclohexane ring are equivalent. So whatever is the carbon you choose with which you attach the wedge, it doesn't matter anything. Okay. Some more IUPAC nomenclature rules we will see. Until now, all the examples that you have seen, it is only for monohydric alcohols. But what about polyhydric alcohols? That we will see now. If you want to do the IUPAC nomenclature for polyhydric alcohols, now the E of the alkane is retained. Okay. Remember all the examples that you have seen in the last slide. Here, look at the IUPAC names. Propan 1 all. That means we have not written PRO PANE. We have simply omitted the letter E. PRO PAN. But now when it is polyhydric, it will be retained. Try to understand the difference. And ending is always with all. Now as it is monohydric, polyhydric, more than one wedge group will be there. So number of wedge groups will be indicated by the addition of prefix such as di, tri, etc. before all. So if it is 2, it is diol, if it is 3, it is triol, like this. Position of wedge groups are indicated by appropriate locus. Now look at the examples. The simplest example that is possible, ethylene glycol, but IUPAC nomenclature is 1, 2. You can also do the numbering as 1 and 2, but actually it will create the same thing. Okay. Root word is 2 carbon, so that is why it is ethane. But see, this E is retained, unlike the previous examples of all the monohydric alcohols. 1, 2 ethane diol. Then we have 3 carbon, but only 2 carbon containing 2 H group, and numbering will be from this side because we have to give minimum number to the carbon with which OH is attached. So if you do the numbering from left hand side, that is like this, 1, then 2, then 3, then it will be wrong. In that case the name will be 2,3-propanediol, but 2,3 is not accepted because when 1, 2 positions are available, why you will write 2, 3? Because that will be the you are not giving minimum number. Okay, so that is why this is not correct. 1, 2 propan, see this E is written, then diol. Next, see this is also 3 carbon, but now the position of OH are different, and whatever number you put, it will always be same. That is whether you start 1, 2, 3 from left to right or right to left, it will always be 1, 3. 1, 3 propene, it will be propane. Propanediol. Okay. Next we have a one ring structure. Here it is actually symmetric structure, so you can do the numbering either this or the opposite, it doesn't matter anything. But here we have both the OH group towards the same side. Okay, that means it will be cis 1, 2 cyclopentanediol. is, all these are not methyl groups, these are hydrogen. Do not have any substituents, right? So cyclopentane, that is the basic structure, and here 2H group present at 1 and 2 position, both are on the same side, so cis 1,2 cyclopentane diene. Fine. Preparation of alcohols. How we can synthesize alcohols? There are different methods by which we can do so. Okay. The first method is hydrolysis of halides. Hydrolysis of halides, in the chapter that we have discussed before starting this one, that is haloalkane, haloadenine, there we have already seen this. Okay, so this is examples of substitution, that is halogen is substituted by OH group. So hydrolysis of halides, so when we are talking about hydrolysis, so obviously we will use some aqueous solution. Here what we do, alkyl halides, they are boiled with aqueous solution of alkali hydroxide. It may be KOH, it may be NaOH, but aqueous solution, because it is hydrolysis. So it is giving us ROH starting from RX. So X is replaced by OH. This is substitution, nucleophilic substitution mechanism, because here the nucleophile is basically HO minus, and from KOH this HO minus is generated, but actual nucleophile is HO minus. So that is it, is nucleophilic substitution mechanism. Examples. So this is 1 degree alkyl halide, and in this case SN2 mechanism is preferred, and SN2, SN1 mechanism, all these discussed in detail in haloalkane chapter, so you can refer to that another chapter if you want to get proper ideas about SN2 and SN1. Fine. So when it is 1 degree alkyl halide, SN2 mechanism will be preferred, and SN2 mechanism polar aprotic solvents are used. This is the nucleophile HO minus, and we are getting RCH2OH. Next example is 3 degree substrate, because see here the carbon with which chlorine is attached, that is attached to 3 more alkyl group, so that is it is 3 degree substrate, and here we are not using any KOH, we are simply using water. Here also here the H2 is directly acting as nucleophile. Product is again substitution, but remember, compared to H2O, obviously HO minus is better nucleophile because it is already carrying some negative charge. But water molecule, it is neutral. Here the electron density is also present, but it is in terms of lone pair, not fully developed negative charged. Fine. Now in case of SN1, what type of nucleophile you are using, even if it is weak nucleophile, it is not important. And why it is not important, that discussion is done in detail in haloalkane chapter. Fine. Because here in case of SN2, the concentration of nucleophile matters, so that is why the nucleophile that you are taking, that must be good nucleophile. So that is the reason in SN2 we are using HO minus, but in SN1 you can use also weak nucleophile, it doesn't create any problem. Second method is starting from aliphatic primary amine. Aliphatic amine, it must be primary. So when it is treated with nitrous acid, that means HNO2, primary alcohol is produced. But remember, HNO2 is not very stable molecule, it is not used directly. So for the generation of HNO2 directly in the reaction medium, what we use NaNO2 plus HCl mixture. So RNH2, that is the starting material, which is aliphatic primary amine. Why primary amine? Because nitrogen is attached to 2 hydrogen, 1 carbon. So for the generation of HNO2, we are using this mixture. So first there is formation of this type of diazonium salt, Rn2 plus Cl minus, and after that it is treated with water, and finally we are getting ROH. Here the reaction is easily favored towards the right hand side because nitrogen is the side product that is produced, and it is escaping from the reaction medium very easily because it is gas. So that is why equilibrium will be easily shifted from left hand side to right hand side. So this is the second method. Starting material is amine. Specific example, here we have taken ethylamine, that is ethyl group, then NH2, NaNO2 HCl mixture, and it is always done at very low temperature. We are getting ethyl diazonium chloride. But this type of diazonium salt, remember, it is very unstable, so temperature is always kept very low. So N2 plus, it is written here as N2 plus, but actually if you write it completely, it will be like this: N plus triple bond N, counter ion for this positive charge is Cl minus. Now this unstable diazonium chloride, finally it will be that is, this nitrogen molecule will be removed, and in presence of water there will be formation of ethyl alcohol starting from ethyl amine. So in the starting material you have 2 carbon, in the product also there is 2 carbon, because there is no loss of electron. Okay, and the OH, that is a source of oxygen, is basically water, because from water oxygen is coming, and the nitrogen that is present in NH2, that is in the starting material, that will be removed in the form of nitrogen gas. Third method, hydration of alkene. Now there are 2 types of hydration possible: direct hydration and indirect hydration. So when it is direct hydration, water is added directly. Addition of water, that means you can think water as if it is, that is, you can write it as HO and H. So as if it is addition of HO and H across the double bond. Fine. And here H2O plus is mentioned, that is hydronium ion, that is acidic condition. Okay, and for creating acidic condition we use concentrated H2SO4. And remember, it follows Markovnikov's rule. Now what is Markovnikov rules? We will come to that point in this slide only. Indirect hydration. So when it is indirect hydration, the alkene reacts with first H2SO4, not water. And what it gives first? It gives first sulfate, following Markovnikov rule. So look at this example. We have taken ethene, very simple ethylene, very simple alkene, that is ethene. Then in presence of H2SO4, H2SO4, you can think it as if it is H and HSO4. Now HSO4, it is actually O, S, double bond O. So this is HSO4. I am writing it in this way because minus and plus. So one H is added to this carbon. See, now it is CH3, and this part, that is OSO2OH, that is added to the second carbon. But in the second step you have to do hydrolysis, just we have done in case of diazonium salt. Remember, there also we have done the hydrolysis, and ultimately this OSO2OH group will be converted to OH, that is ethanol. So here we are using H2SO4. H2SO4 is added first. Remember, it is in the first case also consider H2SO4 there, SO4 is there, but it is not used in equivalent amount, it is catalytic amount. But in this case you have to use equivalent amount, because for 1 mole of alkene you need 1 mole of H2SO4, right? But we have to know what is Markovnikov rule. When the reagent that we are adding is unsymmetrical. So here the reagent in the first case, direct hydration, it is water. That means it is combination of H and OH. It is not symmetric. One part is H, another part is OH. In the second molecule also H2SO4. One part is H, another part is HSO4 minus. Okay, so this is unsymmetrical reagent. But suppose if you are adding chlorine or bromine to CC double bond, it will be symmetrical reagent, because it is combination of 2 halogen atoms. But in this case it is unsymmetrical reagent. And the alkene also unsymmetrical. Suppose if you think about ethene, this is symmetrical alkene. So it doesn't matter whether the H part or HSO4 minus part it is added to, that is whatever is the addition, whether it is 1 carbon or 2 carbon. Suppose this is 1 carbon, use 2 carbon. So here 2 carbon OSO2OH is attached. But if it is attached to 1 carbon, then also it will be same structure. So for symmetrical alkene, Markovnikov rule is not required. Okay, only when unsymmetrical alkene, then only the question of this rule arises. So the reagent is unsymmetrical, the alkene is unsymmetrical, then only we will talk about this rule. Okay, and the negative part of the reagent. So negative part of water reagent will be HO minus, and in case of H2SO4 it is HSO4 minus. Okay, so the negative part of the reagent will be added to that carbon of the unsaturated part which is having lesser number of hydrogen atoms. Okay, take this example. Here this CC bond, it is not symmetrical because one side there is hydrogen, another side there is methyl. So this is unsymmetrical. Okay, now when we are adding water in presence of catalytic H2SO4, this is direct addition, but H2SO4 is also required because it is acting as catalyst. Now if I am writing it is 1 carbon, this is 2 carbon, so 1 carbon is containing 1 hydrogen, 2 carbon is containing 0 hydrogen. That means it is containing lesser number of hydrogen. So that is why the negative part is attached to these 2 carbon. Now come to the second example. Suppose this is 1 carbon, this is 2 carbon. Now in 1 carbon there is methyl group and there is 1 hydrogen, but in 2 carbon there is no hydrogen, 0 hydrogen. That means this is the carbon with which lesser number of hydrogen, in this case it is 0, attached. So that is why now the negative part is attached to this carbon. Okay, so this is the Markovnikov rule. Now we will have one problem here. The only alcohol that can be prepared by indirect hydration of an alkene. Is it methyl alcohol, ethyl alcohol, propyl alcohol, or isobutyl alcohol? Okay. Now when it is indirect hydration, remember Markovnikov rule is there. Now the alcohols that are mentioned here, this is containing 1 carbon, this is 2 carbon, this is 3 carbon, and this is 4 carbon. Now when it is propyl alcohol you are trying to prepare, first come to option C. So in case of option C, if you want to make propyl alcohol, this is the structure of propyl alcohol. This is the structure of propan-2-ol. Try to understand the difference. Here OH is attached to 1 carbon, but here OH is attached to 2 carbon. These two are not same. So when we are calling it propyl alcohol, by default it is actually N-propyl alcohol, not 2 propan-2-ol. That means you have to synthesize this one. But for that, the alkene that you will take, obviously propene, because 3 carbon must be present. Now in presence of H2SO4, that is indirect hydration, this carbon is containing, that is the middle carbon is containing lesser number of hydrogen, only 1 hydrogen, but the terminal carbon containing 2 hydrogen. So that is why this carbon will be, in this carbon negative part will be attached, see, and ultimately it will be converted to H. So the desired compound is N-propyl alcohol, where OH is attached to 1 carbon, but actually you are getting propan-2-ol. So by indirect method you cannot produce propyl alcohol. But the question is, which alcohol can be prepared by indirect hydration? So this is not the correct option, right? Next we will see, if you are trying to make isobutyl alcohol, this is the structure of isobutyl alcohol. 4 carbon must be present because it is butyl. And why iso? Because of the presence of this Me2CH group. But total number of carbon is 4. Now for preparation of isobutyl alcohol, that is this molecule, you have to start from 4 carbon alkene. Now 4 carbon alkene, here we have taken this molecule, isobutene, and here these 2 carbon if we consider, this is the carbon with which there is no hydrogen, but here we have 2 hydrogen. So that is why the negative part will be attached to this carbon, ultimately it is converted to OH. So you are trying to prepare isobutyl alcohol, but what you are getting 2-methyl propan-2-ol. 1, 2, 3. At 2 position there is methyl substituent, so that is why it is 2-methyl. So desired product we are not getting, right? And even that is, we have started from isobutene. And if you are thinking why not start from this type of alkene, now see, this is symmetrical alkene, so OH will always, the product that you will get, it will be always like this, but this is not the desert molecule, so that is why we have not started from this alkene. So C and D are not correct option, that is clear. Now if it is methyl alcohol, it is consisting only one carbon, so you cannot prepare it by hydration of alkene. So indirect or direct method, that will come in the second point. First you have to understand whether by hydration process of alkene can you make methyl alcohol. No, because here starting material is alkene, and for alkene you must have minimum 2 carbon, but 2 carbon is not possible, here only 1 carbon. So that is why methyl alcohol cannot be prepared by hydration of alkene either by direct or indirect method. Next, propyl alcohol and isobutyl alcohol we have already seen. It cannot be by indirect hydration method because secondary alcohol will be formed, because propan-2-ol is the secondary alcohol, but this is 1 degree alcohol. And for option D, this is also primary alcohol, that is the alcohol that we want to prepare, it is 1 degree, but ultimately the alcohol that we are getting, that is 3 degree, because it follows Markovnikov of addition rule, and secondary alcohol will be formed. Sorry, it is 3 degree. It is 3 degree. Okay. So first option is not correct, C is not correct, D is also not correct. But when it is ethyl alcohol, then the starting material is H2C double bond CH2. That means ethyl is 2 carbon, so starting material must be 2 carbon. Now this is symmetrical alkene, so whether the negative part is attached to this carbon or this carbon actually doesn't matter anything. So this is the only alcohol that can be prepared by indirect hydration of an alkene. So this will be the correct option, that is ethyl alcohol. Okay. Now number 3, see, when we have started hydration of alkene, this is actually 3. Under this is Roman numeral 1, then 2, and now we have 3. So this is also example of hydration, but this is hydration by, there is a specific name for this. This is also named as hydroboration oxidation method. But ultimately this is also hydration, that is the net result that you will get, that is also addition of H and OH, but it is not directly we are using water or H2SO4. Okay. So alkenes, when treated with diborane is B2H6. Remember, 2 monomer unit BH3, if attached together it is B2H6, so it remains as B2H6, monomer doesn't exist. Okay, so that is why for the source of BH3 it is always written diborane B2H6. First it will give alkyl borane. So here the starting material that we have taken is 4 carbon in presence of BH3, and here solvent is used tetrahydrofuran THF. Here H, BH3 you can think as if it is H and BH2. Okay, so H will be attached to this carbon and BH2 is attached to this carbon. Okay, so the carbon with which higher number of hydrogens are there, BH2 is attached to that carbon. Okay, so this first step is basically hydroboration. The second step, that is actually oxidation, because in the second step what we are using hydrogen peroxide alkaline medium. So now the BH2 group that is converted to OH. So ultimately the OH group is attached to 2 carbon. Okay, and 2 carbon is containing higher number of hydrogen, 1 carbon is containing lesser number of hydrogen, that is in this case 0 hydrogen, but negative part is added to other carbon which is containing higher number of hydrogen. That means it is not following Markovnikov rule. Remember, if you want to get alcohol, that is, suppose you want to make this alcohol and your starting material is this, so in this case you have to use hydroboration oxidation. You cannot use water or H2SO4 because that will give you OH attached to 1 carbon, but that is not your desired product. Okay, so if we want to get anti-Markovnikov addition, we have to apply this method. Now some specific example we have taken. Propene, so see, CH3 CH double bond CH2, this is diborane. BH3 whole 2. So BH2 is added to this carbon which is containing higher number of hydrogen, and in the second case, now see this compound, this can behave as if it is RBH2. Now RBH2 is also equivalent to BH3, where the R group is, you can compare it with hydrogen. So just you have added BH3 to CC double bond. Now you can also add RBH2 to CC double bond. Okay. So that is why now what will happen? Again the BH2 unit that will be added to this BH unit. Better we say RBH unit, because RBH2 it is actually combination of H and RBH. So in the when you have used BH3, it is combination of H and BH2. Now it is H and RBH. So H and RBH, it will be added to this. Okay. So in this carbon there will be addition of RBH, and in this carbon there will be addition of hydrogen. Now when it is added, still one more hydrogen is there. Okay. So another alkene. So total 3 alkenes are added. This is number 1, this is number 2, this is number 3. So total 3 alkenes can be added, because ultimately it will be conversion from BH3 to R3B. So all the hydrogen will be replaced by R group. And what is R group here? R group is CH3, CH2, CH2. This part. Ultimately we are getting R3B. This is R3B, and this is the step which is called oxidation, because hydrogen peroxide alkaline medium we are using. Ultimately we will get 3 molecules of alcohol. Okay. So all these 3 R group, from this 3 R group we will get 3 alcohol, and the fate of boron is BOH whole 3. Fine. So this is the example of hydroboration oxidation. Number 4. So number 3 is hydration, where we have seen direct hydration, indirect hydration, and lastly we have seen hydroboration oxidation. Number 4 is reduction of carbonyl compounds. Now when we are talking about reduction, first we will see reduction of aldehyde and ketone, because there may be reduction of some other carbonyl compounds, that is also possible. So number 1 point is reduction of aldehyde and ketone. They are reduced to the corresponding alcohol by the addition of H2 in presence of some catalyst, and this method is known as catalytic hydrogenation. Normally the catalyst that is used in most cases is finely divided metals such as palladium, platinum or nickel. See, this is the example. We have taken ketone RCOR. This is general structure. You can consider these as a specific example. CH3COCH3, which is nothing but acetone. In presence of hydrogen, nickel or PT, we are getting 2-degree alcohol. Okay. And you can also use aldehyde and ketones, and the reducing agent can be sodium borohydride NaBH4, or it may be lithium aluminium hydride, instead of taking hydrogen in presence of metal catalyst. So here that reagent is also mentioned. So either use this one, or lithium aluminium hydride, or sodium borohydride. Okay. So if it is aldehyde, you will get 1-degree alcohol, because in that case one of the R group will be H, and if it is ketone, you will get 2-degree alcohol. Okay. So this topic will finish in the next class, because it will take time. So now we will finish the session. So remember number 4 point, we will continue it in the next class. Thank you for listening.